Okay. So, in the last class we are discussing in here this slide. So, we are say this Wn, this product can be simplified to 1 WL LP and WM MQ. So, instead of this one I can write down this is nothing but a WL LP, WM MQ and WN NQ, N into LQ will be as it is. So, WN LQ and this part is 1, this part is 1. So, this part is nothing but a 1. So, I write down the simplified form of the W using the periodicity property of discrete Fourier transform. Now, if I compute, if you see here, where is the L on? L has only WL LP and WN LQ. So, I can say these two things. So, let us say this one does not have any L, this one does not have any M is not involved here. So, I can say this will be go outside of the summation of M part. So, what I said, although I store the data in column wise, I will first access the data in row wise, because M is nothing but represent the row. Although I store the data x0, x1, x2 up to xl minus 1, but I access the data in column wise, compute the first DFT. So, I compute the first rows discrete Fourier transform whose order is M. Is it clear? So, what is, although I store the data in column wise in a 2-dimensional array, now I compute DFT row wise. So, I access the one row data and compute the discrete Fourier transform of order M. Then I I do it. Once I do it, then I take the all column, all row wise DFT is calculated first. Then I do column wise DFT for L, which is the order L. So, if you see that I have a data x of n, I store the data column wise, then I access the data row wise and compute the DFT. So, this row is computed, this row is computed, this row is computed. Now, I again compute column wise DFT. So, access the, so see that how the data is, it is not I am taking the data from 0 to L minus 1 for first DFT. So, I access the data in row wise, when I store it in column wise and then first compute the DFT. So, 2 times I am computing the DFT, first time is order is M, second time is order is L. So, whole algorithm has in 3 steps. So, step 1, compute M point DFT for each row. For each row, compute M point DFT, which is nothing but a f of LQ. So, after this I can get f of LQ. L is fixed, only Q is done. Now, when I do L, so now I get this one. Then define GLQ, which is nothing but a product of NLQ, WNLQ multiplied by FLQ. So, I first compute the DFT row wise, then multiplying each of the coefficient, each of the x value with a value of WNLQ, where L is also varies from 0 to L minus 1 and Q is varies from 0 to M minus 1. Okay. So, this product is done, then I compute L point DFT. So, then I compute column wise DFT to get the output in row wise. The output of the discrete Fourier transform will store in row wise. Because I have said x of L PQ is stored in row wise. Mapping function I have taken like that way. Now you see what is the computational complexity. You may say the process is very clumsy. So, whether it will be computationally easy or it will be computationally more complex. Now, if you see how many complex multiplications are required in first step. So, M point DFT, M point DFT. So first step is required, sorry, this will be not L, this will be M. M is varies from 0 to M minus 1. So, there is a mistake. M is varies from 0 to M minus 1. So, first step we have computed M point DFT. So, we have computed M point DFT for every row. How many rows are there? Sorry, this will be, so this is DFT is M equal to 0 to M minus 1. But how many time I have to compute this DFT? L time. So, L is varies from 0 to L minus 1. So, I said I store the data in column wise and compute DFT for each row. How many rows are there? There is nothing but a L number of rows are there. So, for every row, what is the complexity of the DFT? Capital M. So, how many, what is the complex, so computing M point DFT, how many multiplication is required? M square multiplication is required. So, M square multiplied by the L is total number of multiplication required for computing M point DFT of each row. Again, I will explain it taking an example. Okay? So, I can say M square L is the computational complexity, and how many addition is required is nothing but a Lm into M minus 1, M into M minus 1 for each row. How many rows are there? L number of rows are there. So, multiplying by L. Now, step 2, what is the computational complexity? I have to multiply Wn LQ with this FLQ, both are complex. So, I require M into L number of complex multiplication. Then in start step, here I am computing DFT column wise. So, for each column the computational complexity is L square, there is a M number of column. So, computational complexity L square M. Computational addition is number of addition L into L minus 1 for each DSP, and the DFT, there is a M number of DFT. So, M into L minus 1. Now, if I compute the total computational complexity, total number of multiplication for row wise M square L, for second stage ML, for third stage column wise L square M. So, if I take the ML is common. So, it is nothing but a M plus L plus N, which is nothing but a N into M plus L plus 1, which is not N into N. It is less than N into N. Why? Because if I say N is not a prime number and it can be divided into L into M. So, let us say N is equal to whatever the example I have given 200. So, M is equal to let us say 50, then L is equal to 4. So, if it is N square, then it is 200 into 200. Now what is the number of computational complexity here? It is 200 into 50 plus 4 plus 1. So it is nothing but a 200 into 55, which is much less than this one. So this is much less than this one. So this n square is much greater than compared to this one. Similarly, how many total addition is required? Only 2 stage addition is required. Second stage I does not have required any addition. So Lm into m minus 1, ml into l minus 1. So I can say n into m plus l, sorry, this will be minus 2. So I can say n into m plus l minus 2. So what is nothing but in this case example, it will be n means 200 into 50 plus 4 minus 2 is equal to 200 into 52, which is much less than n into n minus 1. That is nothing but a 200 into 199. So I am reducing. So somehow if I able to implement this way, that divide and conquer methods, I am efficiently compute the discrete Fourier transform, which is much less multiplication complex compared to the first one. But what is required? I have to store the data in column wise, then I have to compute discrete Fourier transform row wise, accessing row wise first, then column wise. So it is 2-stage process. Or I can say I can store the data row wise and first compute the discrete Fourier transform column wise and then row wise. So if I store the data column wise, I have to first compute row wise. If I store the data row wise, I have to first compute column wise. So there is a 2 algorithm is possible. So algorithm 1, store the signal column wise, compute m point DFT for each row, multiply the resulting array by an phase vector W n LP LQ, and then compute the L point DFT for each column. Read the resulting array row wise. Read the result row wise, because I said when I write x, p and q, so k is in the form of p plus LQ, or sorry, MP plus Q. That form we have taken for that mathematical derivation. This form we have taken here, MP plus Q. So that's why the output will be stored in row wise. Now you can say the store the signal in row wise. So here k is this form and n is L plus capital M, capital L into M form. Here I can reverse that. N is equal to capital M into L plus small m and k is equal to p plus LQ. Store the signal row wise, compute the DFT column wise, multiply by W and compute the m point DFT row wise, and read the result column wise. So both are possible. So let's give an example for your better understanding. So let's an example for this purpose. So let's say I have a x of n and I want to compute discrete Fourier transform of n, then I get xk. Let's say n is equal to let's say 32 or let's say 25. Let's say 20. Purposefully I am taking 25. N is equal to 25. So if n is equal to 25, how can I express n in term of m into l, product of two numbers? So n is a non-prime number. So I have to express in m into l form. So I can say no, if I say this is both sides, okay, let's say 5 into 5, both sides will be equal. L and M both sides will be equal. So instead of equal, I want to take, let's say 32, let's say 32. So 32 means I can express in 8 into 4. So n is equal to 32. So 32 can be expressed, 32 is equal to 8 into 4. So I can say m is equal to 8 and L is equal to 4. So if I want to compute, apply divide and conquer method, so I can say if I want to store the data, so there is a m number of column 1, 2, 3, 4, 5, 6, 7, 8. So there is a 8 column starting from 1 to 8 and there is a 4 number of rows 1, 2, 3, 4. Now I have to store my x of n. If I store my x of n row wise, so there will be an index 0, 1, 2. So I am writing only the index 3, 4, 5, 6, 7. So first 7 sample will be written in first row. Second 7 sample, that means 8, 9, 10, 11, 12, 13, 14 and 15. Then I have a 16, 17, 18, 19, 20, 21, 22, 23. Then 24, 25, 26, 27, 28, 29, 30, 31. So n is varies from 0 to n minus 1 means 31. So 31 sample I have written. So I have written the sample in row wise. I can also be written the sample in column wise. 1, 2, 3, 4, 5, 6, 7, 8. 8 column and 4 rows 1, 2, 3, 4. 1, 2, 3, 4. So again I can write like this way also 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So those numbers are representing the index. So basically this is x0 and this is x1. So I store the data, this in this case row wise, in this case column wise. Okay. So I just store the data row wise and column wise. Both I can possible. Let's say I want to compute when I store the data row wise. So if I store the data row wise, first step is to compute DFT column wise. So first column DFT I have to compute. So I have to compute DFT for this column. So if I want to compute this column DFT, so after computing DFT, I will store the DFT in that same column 1, 2, 3, 4. So I access those sample, that means 0th sample, 8th sample, 16th sample, 24th sample. I access those sample and compute 4-point DFT. So I am computing, first step is to compute 4-point DFT. Let's try to go to the next slide. So here, so I am computing first step, 4-point DFT of column wise. So, the data is in red color. So, let us say first column data. So, this is the 0th index data, this is the 8th index data, this is 16 index data, this is 24 index data, I think so, yes. So, this data I have taken and I am computing DFT, discrete Fourier transform of 4 point, where that means L is equal to 4. Now, so what I will get? I will get transform data. So, transform data is also stored in a column. So, this is x0, x1, so index is 1 capital X, 2, 3. This will be multiplied with WNLQ. Okay. So, instead of here LQ, yeah, so here will be MQ, because I am computing column wise, so it will be MQ. Then the again data will be stored in column 0, 1, 2, 3. Now again for the next column data, then for the next column data. So I have how many columns? There will be 8 columns. So there will be 8 such columns. Now I am computing DFT of row wise. So here data is stored in row wise. First compute the DFT in column wise, then I am computing DFT row wise. Then again, so when I computing it, so what I will get? I will get first row, so 4 point DFT. So first, sorry, 8. There will be 8. There will be how many? How many columns are there? So in column there will be in each row there will be 8 cell. 1, 2, 3, 4, 5, 6, 7, 8. So when I computing DFT in row wise, so I have to compute 8 point DFT. So I get again, let us say 8. So first row, second row, third row, fourth row I will get, and then I have to access the data x of, when I representing x of PQ, or when I said x of K, then this will be 0, 1, 2, 3, 4, 5, not 6, 8. It will be not like that. It will be, since I stored the data in column row wise, it will be 0, 1, 2, 3, 4, 5, 6, 8, 7, 8 like that. 0, 1, 2, 3, 4, 5, 6, 7, then 8, 9, 10, 11, 12 like that way. That way I will get how many xk? Xk also varies from 0 to 31. Now, have I get the computationally efficient algorithm or it is not? So, how many multiplication is required in this stage? It is n cross n. So, n is what? Length of the DFT is 4 point. So, for each DFT I required 4 and 4. How many columns are there? There is a 8 column. So, I can say 4 into 4 is 16. So, for each column I required 16 number. So, 8 column I required 16 into 8 number plus what I required? I required a L into M number of multiplication in here also. Once I get that matrix, I require L into M number of multiplication. So, I required here also L, so M is 16, what is my M? M is 8 and L is 4. And in last stage, for each row I have to compute 8-point DFT. So, each DFT computation is 8 into 8, and how many rows are there? 4 rows. So, plus 8 into 8 into 4. So, what it becomes? 16 into 8 plus 32 plus 8 into 8, 64 into 4, and this is 16. If I say that 32 is, if it is 32, if we have taken out, then it is become 16 into 8, so it will be become 4 plus 1 plus 8. So, it is nothing but a 32 into 13. Okay. So, if I take the 32 is common, so it will remain 4. 16 into 2 is 32, so remain 4. 32 go out 1. This will be 32 go out, remain 2. So, 2 into 4 is 8. So, 4 plus 8 plus 1. So, it is nothing but a 32 into 13. If I directly compute DFT, what is the computational complexity? 32 into 32. 32 into 32. Which is much less. Here it is much less. So, I have efficiently computed the DFT using this divide and conquer rule. Now, next class I will talk about the radix algorithm. Here I am talking about the divide and conquer rule. I use the same principle, but I use different radix to efficiently compute this same principle. I will use periodicity and symmetry and divide and conquer rule, and then I will implement fast Fourier transform, which will be much more efficient. You can say this will come in the order of n log 2n, or if it is radix is 4, then n log 4. So, 4n, that I will show you. So, what I will discuss in the class, in this syllabus, I will discuss radix to full, that time dissemination and frequency dissemination radix to full, and I will just touch the radix 4, because radix 4 may not be that much of required. Most of the cases we implement radix 2 algorithm. Okay. So, thank you.